What's up, AP Stats? Chapter 14 notes, page 3 and 4. We did page 1 in class on Monday. Page 2 was kind of homework for you guys, so here's the answers for page 2. Check them. Pause the video if you need to, because I will be moving on to page 3 and 4. Alright, so page 3, we're continuing with that same problem from before, where we're talking about Americans and having a home phone, cell phone, or both. But now we're adding two new concepts. We're adding this conditional probability and independence thing. So the first question says, what's the probability that an American has a cell phone given that they have a home phone? All right, so I'm first going to go back up, take this Venn diagram. I'm going to cut it out. Copy this image and paste it down here. All right, so this should help us answer this question. So what's the probability that an American has a cell phone given that they have a home phone? When you see the word given, it's a pretty big indicator that we're going to want to use this conditional probability formula. This conditional probability formula says this: the probability of A given that B has occurred can be found by taking the intersection of both events and dividing it by the probability of B. All right, so hopefully this makes sense when we do this example. I just want to add a little notation stuff here. Whenever you see this this little thing, this reads as A given B. Okay, so in this case, what's the probability that an American has a cell phone? So we're looking at probability of a cell phone given that they have a home phone. All right, and we can find this by taking the intersection of both. And since our given was that they have a home phone, we're going to divide by the probability of having a home phone. Okay. And then this, these two probabilities I can just get from our picture, right? This top piece, the intersection of a cell phone and a home phone, that's where they both occur. It's 0.58. And the bottom piece, the probability of having a home phone. Keep in mind that's the entire probability of having a home phone. So that is this entire circle, right? What's the probability in general somebody has a home phone? Well, that's 58%. No, not 58, sorry, 73%. Okay, and if I actually did this, 0.58 divided by 0.73, we get about 0.795. So again, what we're doing, guys, is we're taking our whole probability space, like this entire, should be a rectangle, that rectangle, and we're cutting it because we don't care about the entire thing. Now we only care that we're only looking at the people that have home phones. That's why it said, what's the probability that someone has a cell phone given that they have a home phone? So really, in this picture, you don't have to do this, but what we care about literally is just this. We only care about the given piece. And the question said, what's the probability that someone has a cell phone, which in this case, of this circle, these are the only people that have cell phones, given that we have a home phone. And when I said given that we have a home phone, that's why we're only looking at the people that have a home phone. And that's why you can see that this 0.58 needs to get divided by the entire circle. And that'll give us the percent, I know it doesn't seem like this little yellow piece is about 80% of this whole circle, but it is. So that's conditional probability. This will be given to you on the formula sheet for the AP test. Independence, we've talked about two events being independent before. For example, how I perform on a test, that event, the probability that I do well on that test, that's independent of the weather outside, right? Whether or not it rains or snows or is a sunny day, that should be independent from my grade on that exam. Oops. So what this means is that the knowledge of event A does not change the probability of event B. And we can check this using this formula. So there's a little check for independence. Now I switched my A and B around. It doesn't really matter. But basically, to check for independence, the probability of B should be the same thing as the probability of B given that A happened. So like this is saying, guys, going back to my example with that test, the probability that I do well on the test should be the same as the probability that I do well on a test given that it rained. Over here, it doesn't matter. It could rain or snow or whatever. Over here, it's saying given that it rained, like it should be the same. It shouldn't affect. And if these two probabilities are the same or somewhat the same, we can say that they're independent. So letter B here is asking us, are the events of having a cell phone and having a home phone independent? I mean, just think about this yourselves. Like, do you think that having a home phone affects whether or not you have a cell phone? And I did myself, I'm thinking, yeah, they should affect each other, right? I think people are less likely to have a home phone if they have cell phones, but we'll see. Let's actually use the probability statements here. So let's say the probability of having a cell phone given that we have a home phone, is this the same, I'm just using this independence formula, as the probability of just having a cell phone? All right, and we can just take these from our picture. This one we actually already did. The probability of having a cell phone given a home phone, that was what we just found. So that's 0.795. And now the probability of having a cell phone, just a cell phone, we have 83%. All right. So we can see here that just generally speaking, there's an 83% chance that someone has a cell phone. But now if they have a home phone, that probability shrinks down to below 80%. And these are not equal to each other. So we say that these are not independent. All right, we can see that somehow having a home phone is affecting the probability. Okay, letter C says, are the events of having a cell phone and having a home phone disjoint? Remember what disjoint means. Disjoint looks like this, that there's no possible way for someone to have a home phone and a cell phone. These two events cannot overlap. So is this true? No. These events are not disjoint. They can both occur at the same time. Okay. We talked about this already before. Can disjoint events be independent? Remember, disjoint is something that looks like this. There's no overlap. Independence, on the other hand, there is overlap. All right, and there's a proof to this. I'm not going to show you the proof for time's sake, but just know that disjoint events are not independent, right? You're either disjoint. Remember, you can also use the term mutually exclusive. But disjoint events are not independent. So these two events can be one of three things. First, they can be independent. Oops. Which means they're not disjoint. Two, they can be disjoint. Or three, they can be neither independent nor disjoint. And we'll see examples of this later. Nothing too crazy there. All right, so before we do these practice problems, just a quick recap of what we've done. Conditional probability and testing for independence. All right, conditional probability is really just probability, guys, but we're looking at a smaller sample space. All right, so like if I said, I'll give you another quick example. Hey, what's the probability that a student at Round Lake High School likes the color blue? All right, so we're looking at all the Round Lake High School students. But what if I said, hey, what's the probability that a Round Lake High School student likes the color blue, given that they are in Mr. Zamudio's class? Well, now I'm not looking at every single student anymore. Now I'm looking at the givens. I'm only looking at the kids in my class. And from those kids, I have to see who likes blue. That's all conditional probability is. Independence, you should know that like one event should not affect the other event. Like the probability of that event should be the same as that event happening given that another event happened. This is how we know that they're independent. And we saw the example with the cell phone here. Like these two events were not the same. Okay. So practice for this one. In its monthly report, the local animal shelter states that it currently has 24 dogs and 18 cats available for adoption. 8 of the dogs and 6 of the cats are males. Find the following probabilities. What is the probability that a randomly selected animal is a female dog? So for this one, I'm actually going to go ahead and make a two-way table. Let's do this. 2 cats. Do dogs. Do male, female. And let's include the margins. We'll make this a marginal table. Okay, so we know that we currently have 24 dogs and 18 cats. So the total for dogs, 24 total cats. 18. Well, I can add this across and get this total. So I think in total we're dealing with 42 animals. Some of which are cats, some of which are dogs, some of which are male, some of which are female. They tell us that 8 of the dogs and 6 of the cats are male. So dog male, there's 8. And cat male, they said there's 6. So using this, we have a total of 14 male animals. And again, this is just kind of intuitive here to figure out, okay, so if we have 18 total cats, 6 of them are male, how many are female? We have 12 there, same logic over here. We have 16 female dogs, and adding across 12 plus 16, we have 28 female animals in total. Okay, so remember, the inside of our two-way table should add up to the total. So these 4 numbers should add up to 42. 6 plus 8 is 14, 14 plus 12 is 26, 26 plus 16, 42. And then the margins definitely add up. All right, so we know we constructed our two-way table correctly, so hopefully this helps us with this problem. What is the probability that a randomly selected animal is a female dog? So in this case, we're just looking at what's the probability that they're female, right? So in total, all the females, we have 28 out of all the animals. So all the animals, they're 42. Right, and I can... Did I look at that correctly? No, I did not. Oops. I will cut. All right, so now that we've made our two-way table, let's see if it helps us with these questions. So question A says, what's the probability that a randomly selected animal is a female dog? So we're looking to see for female dogs. We have 16 female dogs out of all the animals. 42. All right, and if I did this in my calculator, it's about 0.381%. Okay, so that was just a regular probability question. Question B says, what is the probability that a pet is male given that it is a cat? So now this becomes a given conditional probability statement. So we're looking at the probability that's male given that it is a cat. And we can find this by taking the intersection that it is both a male and a cat, dividing by the probability that it's a cat. And this is just, what's it called? This is just that formula, just substitute it in for male and cats. Okay, so the intersection of males and cats, well, I have 6 male cats out of 42. Let's say 6 out of 42. That's the probability. Now, what's the probability that we have a cat, that we pick a cat out of all our animals? Well, there's 18 cats out of 42 total. And what you see here, when we do these probability charts, these two-way tables, is the denominators actually end up canceling each other out. It's really just 6 out of 18, which is 1/3. about 0.3 repeating. All right, so the probability that we pick a male given that it is a cat is 33%. And looking at this two-way table, picture this, guys. It's almost as if you're cutting part of this table out, right? We know that we're given that it has to be a cat, so we're literally just looking at the cats. So ignore this. And now it's that same question. What if I said, hey, what's the probability that we get a male? Well, it's 6 out of 18, which is 33%. All right, C, what's the probability that the pet is a cat given that it's a female? So probability that's a cat given that it's a female. So again, first look at the intersection. That's a cat and a female. And then you divide it by the probability of being a female. Okay, so the intersection of cats and females. So cats, females, there's 12 out of 42. I'm just going to put 12 because I know the denominators cancel out anyway. And then the probability of being a female. So in total, we have 28 female cats, or female in general, cats or dogs. So 12 out of 28, we get 0.429. All right, so the question here says, are the events of pet type and gender independent or disjoint? So can I have a cat that is a male? Can those two things happen at the same time? Can I have a dog that is a male? Can I have a dog that's a female? Can I have a cat that's a female? Those things can all happen at the same time. So these are not disjoint. These are independent events. All right. And we're going to check that using this independence thing. So the probability of B given A should be the probability of B. So I'm just going to pick one here. So let's say the probability of being a cat given that you're female should be the same as just the probability of a cat. We're checking this. I picked this one because we actually just solved that one, right? We did that for letter C. So this is 0.429. And then the probability of being a cat, we have 18 cats out of 42. 18 out of 42. If you did 18 out of 42 in your calculator, this actually ends up being 0.429. So yes, they are independent, and we know that because we checked using our independent rule.